Oh, I was about to record. Rav, what's your question?
Yeah, something wrong with my computer. I'm just gonna restart and come back in 5 minutes.
Okay, thanks for letting me know. Hello all, welcome to another adventure together. This time around we're going to connect together the world of magnetism and the world of electromagnetism. See how they all unite together. All right, first off, just a bit of history with regard to magnetism. There are many cultures that have discovered this crazy magical property. In fact, there's a type of stone that can magically attract ferromagnetic material to it. And this type of stone is called lodestone. All right, looks like an ordinary stone, but it is ferromagnetic. All right, and there are cultures that figured out that if you took this and you suspend it on a string, it'll always orient itself in this dimension, which so happens to be the north-south dimension, and that's how they invented the first compass. All right, so they discovered that Earth has a permanent magnet, and these things like to attract themselves and line themselves up with Earth's magnetic field. Again, text in blue, don't really need to copy down. But what is important is knowing what field lines look like. All right, so here's an ordinary bar magnet, and to the naked eye, we really can't see these fields that come from it. It's kind of like gravity, right? We know that, for example, in my room right over here, gravity has a vector that is pointing downwards. How do we know? Well, I can just take some ordinary objects like these pens over here, and the moment I let go of them, okay, gravity's pointing downwards here. How about over here? Sure. Towards you guys? Okay. I think we got some conclusive results here. We can see that these fields are all pointing downwards, at least in my room right over here. All right, so how would you figure out how the fields behave in a magnet itself? Well, you'll be doing something very similar as well. You need to have some sort of tracer to figure out where the fields are traveling. One thing just to let you know is that there is a term for these fields. Gravity, they're called gravitational fields. Right? These are just lines that point towards the center of the Earth. And magnetic fields exist as well, and they're commonly known as B fields. So let's go and check it out. Let's have an overhead camera view of what's going on. Beautiful. Here's the overhead camera, and how about I just zoom that in so that everyone can see that nice and clear. Oh yeah. All right. So here's a lovely bar magnet, and there are fields that come from here, and that's the reason why stuff will want to get stuck to it. All right. But we can't see the field lines right now as is, so we need to include a tracer. And one of the best tracers is this stuff over here. It's nothing more than just sawed up iron, also known as iron filings. There you go. Okay. Now, whenever you do this demonstration, do not sprinkle the iron filings directly onto the magnet, because if you do, that means that student's going to stay after school and manually pick off every single iron filing until it's all clean. Then that student can go home. Okay, so don't sprinkle it directly on top. Instead, normally I ask students to go and get a piece of paper and drop that paper on top and then sprinkle on top of the paper. To make things a little bit more awesome, what I found was this old Ferrero Rocher container, and it will do the same job, but also be transparent at the same time so that you could see the field lines coming from this bar magnet. All right, so ready for some magic? And yeah, we may as well cue up the music. Here we go. There you go. All right, so what exactly is going on in this crazy looking picture over here? Well, it looks kind of like that, does it not? I know that this one's probably not the best examples, but you get the idea that you'll see that there are these B fields that leave from one magnetic pole and they come back in the other side. So this is a very crude, messy drawing. So to clean it up, normally in textbooks as well as notes, we draw it like this instead. Okay, so copy down the diagram on the right. And while you're copying down the diagram on the right, keep these ideas in mind. All right, first off, these field lines, we can't see it, and they're called B fields. Some textbooks call it magnetic flux density. I'll stick with the easier term. Now, as for standards of convention, when you look at the picture over here, you can't tell which side's north and which side's south, right? They look symmetrical on both sides. In fact, if I didn't color code the magnet, you wouldn't be the wiser. However, we do know that magnetic fields, they do interact with each other such that like poles repel and opposite poles attract. So there must be a direction with regards to these field lines. So the international standard that we go by is that we assume that the B fields leave from the North Pole, cycle all the way around, and return back to the South Pole. That's our international standard. Another rule that which was covered by Mr. Maxwell, he noticed that these B fields always create a complete loop. So in other words, as it leaves from the North Pole, it'll travel all the way around and return back to the South Pole, but inside of the magnet, it'll complete the loop so they can go over and over again. In other words, with regards to the B field, there is no beginning and there is no end. Lastly, just watch out for this. When you draw out your diagram, stated in your notes, make sure that the B fields do not cross. Okay, keep them nice and clean, like in the diagram on the top right. And yeah, I'll give you guys a minute to jot that down. We'll use the clock as our reference for 1 minute. Sure, we'll give it another minute. Okay, so once again, when you draw this in your notes, again, make sure that your B fields first leave from the North Pole, travel all the way around, and return back to the South Pole. And you'll draw these arrows to tell the reader that the B fields leave from the North and return back to the South. Internally, if you want to connect it, you're more than welcome to do so, because that's what happens inside bar magnets. All right, so the B fields will return from South to North inside the magnet. Okay, so B fields always leave from the North Pole, cycle all the way around, and return back to the South Pole. Make sure that your B fields don't cross. And the reason for that is if you take a look at the picture over here versus what's happening in the field diagram, you'll notice that where all the B fields are closely packed together, that's where the magnetic field strength is the strongest. So as B fields move further apart from each other, the intensity is weaker. And where the B fields are really close together, that's where the magnetic field lengths are the strongest. All right. So if you hypothetically ever had a B field line crossing with another B field line, that means you have a point in space where you have infinite intensity in magnetic field strength. And you can imagine, well, what that will happen with that, right? You've turned into a magneto, and everything that's magnetic will become attracted to you, even from 1,000,000 miles away. And that's why we can't have B fields crossing on top, all right? That's one of the reasons. The other reason is that really the picture over here, it's the superposition of all the tiny little magnets inside the big magnet. Okay, well, we'll talk about what that means later on, but we're looking at the big picture, all right? We're looking at the big picture, and in the big picture, we can't have B fields crossing on top because it's mathematically not possible. In fact, if they were technically on top of each other, then we just simply as a vector has a bigger value because it's the summation of the two smaller vectors. Okay, so we'll never have B fields cross, ever. Any other questions before we move on? All right, so outside of the magnet, the B fields flow from north to south, and inside the magnet, it will return from south back to north again, always creating a complete loop. Okay, so that's of just one lonely magnet. But what happens when we have more magnets with each other? All right, such as the case where you have, similar poles with each other, and what if we have opposite poles with each other? And yeah, we'll do another live demonstration with that. And that's why I wanted to pre-magnetize all my magnets. All right. Normally, with regards to magnets, after the session's over in a course, all the magnets are usually just thrown in a box, and they just sit like this or like that. And eventually, they will compete with each other and ruin their alignment. So they always have to be realigned again before each session. Okay. So first, similar poles repel, and I'll start off with that demonstration. Whew. You can see that happening right here. Let me switch cameras. Okay, yeah, it's always nice to have nice and strong magnets because they do the best jobs. There you go on full screen. Okay, look how strong these magnets are. They really hate each other. Oh yeah, that's beautiful. All right, but I don't want them to completely repel from each other. I just want to set it up, and then I just want to see the corresponding field diagram from that setup. Ooh, it's turning. Stop turning. Okay, let's check this out. Do I really need the music? Well, how about the other music? Let's see what happens in the middle. As I shake, 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 yeah, we'll see field lines over here. That's beautiful. On the far end, we'll see other field lines. But what happens in the middle between these two?
Oh no. Oh no. Oh no, 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 no.
Huh. You'll notice that there are no field lines in the middle, right? There's no iron filings attracted to over there. So that's something to keep in mind when you draw this type of diagram. In fact, let me just switch back. And you can see that in the diagram, it's exactly what happens. Sure, I'll give you guys a moment to jot that down. And then we'll do the opposite poles attract. So again, just be very careful in your drawings. Make sure that your B fields do not cross. Because again, if they cross, that means you have a point where, mathematically speaking, it has infinite magnetic field intensity. But what you will notice in your drawings is that in the complete center, you won't see any magnetic field lines at all. And you can imagine that if you drew this the other way around, where you had, for example, north on the edges and south in the middle, the diagram would look more or less the same. The only difference is that the direction of the arrows would be in the opposite direction. That's the only difference. Okay, now let's set up the other case now, okay? And I'm going to try to set it up so that's in the same orientation as in the setup. So it'll look like that, yeah, as in the PowerPoint. Now you'll notice if I place them too close to each other, they're going to attract. So I need to keep them far away enough that they don't stick. So some distance like that, but close enough together because I want you to see what happens directly between these two. All right. So pretty much the same exact setup. And let's check out the outcome. Cue the music because we love queuing up the music. Oh yeah, disco, disco, disco. Sure, I can zoom in just by a slight bit just so that you guys can take a look at it. Okay, now I gone a little bit overboard over here, but I hope you get the idea right in the center. What you can see is that the magnetic field intensity is much stronger right between these two. All right, so they're going to attract far more iron filings than they normally would by themselves. Okay, just like in the diagram over here. Yeah, I was hoping to get monkeys spinning monkeys, but I haven't had a chance to set that up in my soundboard yet. That would be a funny one for here, wouldn't it be? Do 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 do. Oh my gosh, with that robotic voice. How could that be possible? Okay, so I hope that's enough time for you to jot it down. And here's the thing what I want you to appreciate about these diagrams over here. As I briefly mentioned, what you're seeing really right here is the superposition of the two magnetic fields. All right, because we know that from the North Pole, for example, we have B fields that are leaving from it, and I'll just color it in red. Where's the red? Here you go. Okay, so B fields leaving from it, that which looks something like this. All right, and we know that there are B fields through the middle. But on the right-hand side, we also have B fields that travel in the opposite direction. And if these are two identical magnets, it's of the same intensity. Okay. Now, here's the thing. When you take a look at what's happening in the middle, if you treat B fields as a vector, which is what they are, here's the North Pole coming from the left-hand side, and here's the North Pole coming from the right-hand side. If they're equal in opposite intensity, when you add them together, right, so that vector plus that vector, you end up getting what?
0.
Exactly. You get 0. All right. So they mathematically have subtracted or differenced themselves out or canceled themselves out, if you want to describe it that way. And that's the reason why you'll see no B fields in the middle. Again, it's not that they've disappeared. You're just looking at the final outcome of the interactions of these two magnets, where they net to a value of 0 in the center. And if you take a look at the example over here, we have double power, because coming from the right-hand side, we have B fields moving towards the left. And as you know, with magnetic south, the B fields return back to the left from the South Pole. All right, so with the South Pole, B fields returning back. We have B fields leaving from the North Pole. So when we take a look at the mathematical sum, if one of them is pointing to the left and the other one's pointing to the left, you get double the intensity pointing to the left. And that's why the magnetic field intensity is so strong between these two opposing magnets, which as a result causes them to want to attract one another. And we end up with these diagrams here. Now, as for the scribbled dots down below, do you need to copy these scribbled dots? No, you don't have to. All right. The only one that's actually important are the ones up above. So I hope that you have enough time towards drawing these two diagrams above. Okay. And if you still need a bit more time, that's fine. You can go ahead and jot that away. Let me just show you another YouTube video by another awesome YouTuber, not me, unfortunately, describing how B fields interact.
Today we're going to look at 4 different demonstrations involving ferrofluid and powerful neodymium magnets. Ferrofluid is a liquid that reacts to a magnetic field. It's usually made up of a mixture of oil and tiny iron particles. Most people don't realize that we actually use ferrofluids every day. You'll find them in speakers, motors, even hard drives. But the real fun comes when you get a bottle of the stuff. For the first demonstration, let's try dripping some ferrofluid onto a magnetized bolt. Then
Awesome, even though it's a Monday. Oh, whoa, I almost gave away the secret here. So I'm going to go off and remove these magnets and move them out of the way. Leave these fields over here. And you can see that I have full control over these fields. So I'll check that out. Oh, yeah. Okay, so yes, I do have one of those rare earth magnets, and you don't want to keep it anywhere near anything else. All right. In fact, if you watched the video, I saw I saw the same outcome. Where normally what I do is I tape up my rare earth magnet, because often it gets chipped like crazy. These things are ridiculously strong, and I always tell the students never put 2 of them near each other. And yet, at some point during the school period, somebody will bring 2 of them next to each other, and they'll come together. Not only will they have a blister over there because they pinched their finger during that process, you end up seeing one of these shatter off. All right, so if you watch that video again in the future, you'll see bits and pieces of it chipping off, because these are ridiculously strong, and it's a huge force when they come together. I won't be surprised if it's 30 to 50 pounds or more once they are attracted to each other, because it's very hard to try pulling them apart. Anyway, so many of them broken at school that this is the only last one remaining, so I have to be very careful with this last guy here. Okay, continuing on with the whole idea about magnets, all right? There's this theory, and it's called the domain theory. And as I mentioned with regards to theories, it's a way of explaining how the world works. And it's okay until somebody else says, wait a second, it doesn't cover this. And then they end up making a new theory afterwards. It somewhat did happen with the domain theory, but the interesting thing is that domain theory, it still exists to this day. So we'll still use this to explain the general basics of how magnetism works, because it's a great way to introduce the whole idea behind it. And domain theory simply states that any magnet you have around is really made up of teeny tiny little magnets inside. Okay, and those teeny tiny little magnets, they're called either dipoles or dipole moments, depending on the textbook you read them from. All right. So every big magnet is made up of tiny little magnets. So you could have metal that has not been magnetized yet, kind of like these paper clips over here, right? These paper clips, they do not want to stick with each other whatsoever, all right? But if I'm able to line up all of the little magnetic domains or the little their dipole moments, then yes, it can become magnetized or temporarily magnetized. Okay, so if all the little magnets that make up this big magnet over here are all lined up like in the picture over here, this will become a magnet. Best way to demonstrate that is to take my really strong magnet, place it on top of this paper clip over here, and with that, oh, what I'm going to dare myself in doing, I will do it the safer way, because I don't want to dirty up this magnet here. Okay, so I have this, and with that set up here, just so that you can see it in space, here are my iron filings, and here they are all attracted to it. Okay, and if I take away the strong magnet from it, it will temporarily stick for the first moment because their moments are still aligned with each other. Okay, so there's still a little bit of alignment because they're all in close vicinity. However, because I haven't tempered this properly, the domains will become random the moment I drop it, and you'll see it's lost its ability to magnetize afterwards. Okay, so if you want to magnetize something, especially if it's of some sort of soft iron, it has the ability to become permanently aligned. And what you need to do is you need to take a permanent magnet and you need to swipe it across that temporary magnet enough times. And as long as the metal has been properly tempered, eventually the field lines will all just line up and it'll become a permanent magnet. And that's what I do with these magnets over here. All right, I put it in a very strong magnetic field. Then one side has B fields leaving from it, and the other side has B fields that return back to it, making magnetic north and the return back of magnetic south. So as long as you swipe a permanent magnet through anything that's ferromagnetic, eventually it'll become magnetized when all the domains are all lined up. As what the video has mentioned, only certain elements exhibit this magnetic property, and the three major ones are iron, nickel, and cobalt. All right, if you're wondering what to copy down over here, maybe the domain theory and the three types of ferromagnetic materials, at least the abundant ones. All right. Yes, there are rare earth magnets as well, but we're just dealing with the simplified periodic table. Raise of hands if anyone needs me to keep this up for a bit longer. Okay, I'll wait until those hands are down and then I'll advance on. Until then, I'm going to clean up this place. I don't think I need this stuff anymore. Because believe it or not, these iron filings in this container here, they're older than you guys. Okay, so year after year, we just constantly just put them back into the container and recycle them. They don't go to waste. And if you want to hear some awesome ASMR, oh man, oh, no, the mic is too far away. Anyways, if you can hear it, you can hear it. It's pretty cool, all right? And what I do is that, you know, usually when I have iron filings all over the table, the best way of picking it up, just to make sure you pick up the iron filings as opposed to just dirt, is to put a really strong magnet on the top of a lid and then use that as a vacuum. You can hear all that little vacuuming that sounds, and yeah, it's just like ASMR. So I'll give you guys a moment to listen to it. Haven't done attendance yet? No, I haven't. So just type in hello right now and quietly listen to the ASMR music in your ears. Here we go. Oh. Not sure if you guys can hear that little clicking sounds. Probably not with all the audio compression, all right? But I hear all these quiet little clicking sounds, and that's from all the iron filings finding them way up to where the lid is, and there you have it. And with that, I just quickly place it on top here, pull the magnet away, give it a few taps, and that's how I clean up everything. And we're ready to reuse this again next year. Right. So nope, these iron filings do not get wasted whatsoever. Permanent metal, repeat that again. You mean permanent magnets, all right? Permanent magnets have all their dipole moments all lined up, and they don't disarrange very easily. And yes, you do have to temper the metal properly first. What they do, and you can watch these on YouTube recordings, is first off, they place a piece of metal in front of a very strong north and south pole. Normally it's done with an electromagnet. And while they place in this position, they gradually heat up the metal. All right, so they heat it up till it reaches its Curie temperature, which is a temperature where it's going to lose all its magnetic moments. Then they'll let it gradually cool down. And as it cools down, it crystallizes all the magnetic moments so they're all in proper alignment. And that's how they pretty much create these materials. All right. So it's just a soft iron core, or it could be an alloy. As you'll see momentarily afterwards, I'll have a list to show you guys of the fact that when they mix these metals at a proper proportion, you can create a stronger permanent magnet than using any of these individually. We'll save that for later. Okay, I think I can advance on now, unless if there's any other questions. Okay, so again, even though the domain theory has now been, you know, usurped. Yeah, that's a fancy word. Even though it's been usurped by the electron theory, we'll still keep with the domain theory because, again, it's really good at explaining just the basics of what happens with magnets. All right. So yes, at some point, eventually, anything that is ferromagnetic will become magnetized. And the reason why it's going to become magnetized is because we have a big magnet underneath us, right, which is Mother Earth. Now, here's the thing which is the really weird part about magnets. We know that magnets can only turn if they have an opposing magnetic field. Then it'll become attracted to it, all right? If it's the same field, it's going to hate it and it's going to repel the other way around. So when you think about the Earth, and let me just go ahead and try to draw one. Okay, so you can imagine Earth as this big circle right over here. This is good old Mother Earth over here. The only reason why a magnet will face this way, where north will face towards the North Pole, is if the North Pole was actually magnetic south. Right? So the North Pole is actually magnetic south for this to want to turn in that direction. And magnetic south cannot be south because it will repel away from that magnet there, like so. All right, so we know that Earth south has to be magnetic north. So that's the one trippy thing about our magnetic field here on Earth. Okay, so outside at the surface of the Earth, North Pole is actually magnetic south, and South Pole of the Earth is actually magnetic north. It's the only way to properly line up our compasses. Okay, so yes, if you leave items in this orientation for long enough, eventually they'll have all their magnetic moments lined up with Earth's permanent magnetic field. And remember, the Earth's magnetic field, yes, it's going to come from the South Pole as it's magnetic north. It's going to travel outwards, return back to the North Pole, and inside the core of the Earth, it will travel from north to south. These poor magnets, you can see that they have tape all over them because when students try returning them back to the desk, I don't know what they trip over, but somehow they cause these things to fall to the ground. And as it is very brittle, it does snap. But here's the interesting thing. If I do break this apart right now, I'm not going to break it apart. Can this one break apart? I don't want to ruin my taping job. But you can imagine that if this was one big magnet and I snapped it apart, who do I got? Two teeny tiny little magnets. And that's one of the properties of this domain theory. Because every big object's made up of tiny little magnets, when you snap it in half, you just end up having two smaller magnets. Not that I have it animated, but you can imagine if I take those magnets and I break them in half again, I'll create even smaller magnets, and I can just keep on going at it. The point behind this is that you can try taking a magnet and breaking it as many times as you want, and you'll never end up having a magnet that's just magnetic north. For every north, there's always a corresponding south. Okay, and that's why magnets are often known as dipoles. All right, these moments are called dipoles because there's always going to be two poles. You're never going to have just one. If you're a big fan of the TV show Big Bang Theory, I can't remember if it's the end of season 1, the end of season 2, or maybe even the end of season 3, but there was an episode where all the boys went to the North Pole because Sheldon, one of the geeks on the show, he wanted to prove that monopoles do exist. All right, if you go to the North Pole, I think this is what they did at the end of the season episode, he wanted to prove to everyone that, yes, a monopole does exist. And I'll let you guys watch that episode plus the next season's episode if you want to see the spoiler. All right, I'm not going to spoil it for you guys. Here's the other thing about magnets. Don't drop a magnet, because if you drop a magnet, well, what's happening? You're causing it to bump around, jostle around, and you will cause the magnetic moments to become misaligned. So that's one way of demagnetizing an object, just by dropping it or hitting against a hard surface multiple times, and it'll become demagnetized. Another way of demagnetizing magnets is to get a lighter and just light it up and let it hit its critical temperature, known as the Curie point. No, it's not the same person as Madame Curie. I had to look that up myself. It's a different scientist that discovered it. Okay, so if you hit it beyond, or say if you increase the temperature beyond its critical threshold, remember that as you increase kinetic energy, molecules jiggle a lot more and they're able to more freely move. So once you reach that critical threshold, now the molecules are able to freely move around, the magnetic moments are all freely unattached, and at that threshold, the permanent magnet won't even become magnetized anymore. It's a pretty cool demo. If you have a chance to watch it on a YouTube video, by all means. What they'll do is that they'll have a permanent magnet, usually blocked off and shielded by concrete. All right, so it's going to be very strong, and they're going to put a piece of metal on the other end. The metal, and it'll be attached usually to a string just so it's able to freely move, or they can just let it stick as is. Then they'll take a blowtorch and they'll start heating away at that piece of metal. And you'll notice that once it's reached its critical threshold, it'll just drop. And even when it's on the ground, you put the really strong rare earth magnet near it, it won't do that. It will not become attracted until it cools down below its threshold, its Curie temperature. All right, some magnets are really strong, like my rare earth magnet over here. And some of them are kind of like weak sauce, like this guy over here. And it has to do with something known as magnetic saturation. In other words, depending upon the composition of that magnet, some are stronger than others. And they will reach that critical threshold where no matter how many times I try swiping this from north to south, all right, trying to line up the dipoles, like if I try doing this and I try swiping it across, no matter how hard I try, this guy will never become as strong as this guy. And that has to do with the materials themselves. They will reach a critical threshold called the magnetic saturation. All right, and the fancy words for that is that all ferromagnetic material, they'll reach a maximum magnetic permeability. It's a numerical value associated with either the element or the alloy, which tells you this is as strong as it can get. And often it's just a coefficient. Just like friction. If you recall with friction, if you have a coefficient of 0.12, that's it, 0.12, hard stop. There are no units with coefficients, okay? And magnetic permeability, it's also a list of coefficients as well. So if you take a look at the list on the right, no, you don't need to copy it down, but you'll see that there are no units associated with it, all right? And what this is telling you is that if you compare iron with regards to air, then iron will be 200 times more permeable or stronger at becoming magnetic than air does. So yes, even air can become, or even vacuum space can have magnetic moments pass through it. And that's the weird thing about magnetism. You don't need any materials for magnetic fields to transmit through space. Okay, and as I mentioned earlier, that if you have an alloy again is a composition of different metals, you can definitely improve the effectiveness of that permanent magnet. Any questions so far? Again, you don't need to copy down the chart on the right. That's not necessary. It's just for your reference, and that's it. That there is a numerical value associated with it, and we're not dealing with any of those calculations this year. Okay, let's advance onwards. Okay, so Hans Christian Ørsted is a famous scientist who noticed that it is possible to pass electricity through a piece of wire. Okay, so given a random straight piece of wire like this guy over here, if I connect the ends to a battery, which this is for demonstration purposes. Here's AA. He's going to use something much stronger than a AA. All right. So here's a piece of wire, and if you connect the ends to that battery over there, or that cell, you'll notice that this wire here will start to attract iron filings. Not very well, but it is able to. Now, here's the thing about it. The iron filings won't just stick onto the wire itself, okay? So if I pass current through this, the filings won't just stick to this. Instead, what you'll notice is that you'll end up creating fields around it, all right? And the fields will always be 90 degrees relative to the wire. So if the wire is traveling left to right, what you see over here, the fields will be going either up through the front or down through the front, depending upon the direction of current. And this is where Ørsted's principle comes into play. Hans Christian Ørsted noticed that if you allow current, for example, to travel towards the left, you start using your right hand rule, so physically your right hand, and you let your thumb point in the direction of current flow. And if the current flows this way, in other words, I had it hooked up in this manner, so positive goes over here, and the positive the positive current's able to flow through the wire through here, all the way around. Then at this top part here, the current will be flowing towards the left, and I use my hands to tell the reader that at the top of this wire, the B fields will be traveling upwards. Okay, and if I'm beneath the wire, the B fields will be traveling downwards. And that's because B fields will always create these circles around the wire, like so. So you'll have one B field ring inside here, another B field ring over here, another B field ring further out here, and another one even further out. So these B field lines that are created, they are not in alignment with the wire. Instead, you'll notice that they're always going to be 90 degrees to it, this way and this way. In other words, it'll create concentric circles that are orthogonal around a conductor. Okay, so the magnetic field exists when the current is flowing through the conductor, and the field will always be orthogonal to the current flow. And I'm pretty sure I have a cute diagram somewhere on the right. There you go. So I'll give you guys a moment towards jotting down what you need to jot down over here. And then I'll explain a bit of history about this stuff, and then I'll show you a cool little video of a demonstration of this. Give you guys, I guess, 2 minutes. Cue the music, relaxing music. Okay, I hope that's enough time. Again, just raise your hands if you do need more time than that. But let me just stick with this picture over here for now, just to explain it one more time. Good. All right. So yeah, while you're jotting it down, I just want to explain these pictures over here. So these pictures are all based upon something called the right-hand rule. And if you take a look on this history timeline, I hope it doesn't block off too much of your text, but Oersted's principle was back here in 1820. All right. This is well before J.G. Thomson's plum pudding example, which described that atoms are made up of protons and electrons, which was discovered almost 100 years later, like 80 years later or so. All right. So as I mentioned, a lot of things that we do in science is because it became a standard due to a theory from back in the past. All right. So until 1897, we've been assuming that current has been flowing from positive to negative. So in this unit, we're just going to continue with that wrong theory. Because you got to keep in mind that the whole understanding of volts, amperes, ohms, Kirchhoff's laws, and even Thomas Edison and Nikola Tesla, they all assumed that current flowed from positive and negative. And it wasn't until about 100 years ago that they disproved that. All right, so are we going to go off and delete all of that old history? Probably not, because again, they had positive, conclusive results, and they were true each and every single time. And that's why those laws or those formulas are still valid to this day. All right. So to keep with that trend, since all the research was done back 200-300 years ago, we'll still assume that current goes from positive to negative, even though it's disproven otherwise. Okay. So we're going to use something called the right-hand rule. And again, this is something that, you know, Alessandro Volta, Andre Ampere, and all the other electrical nerds out there, they all follow the same rule as well. And it goes something like this. Let me just rewind back. Okay. Your thumb will indicate the direction of current flow. So yes, that conductor that we have over there, it is connected to a battery somewhere in the distance. Where in this setup over here, the battery probably has a positive at the bottom, because current leaves from the positive end, travels through the conductor, and will return back to that battery again. All right, so in the background, that's where the battery is connected to this. So our thumb will always point to the direction of current travel in that part of the wire. And our fingers will tell the reader which way the B fields are cycling. So you can see in the first example, the B fields are traveling towards the left, behind the conductor, just like how your hand would be if your hand was behind the conductor. And in front of the conductor, the B fields will be traveling towards the right. Okay. And in the second diagram, this is just emphasizing that current and B fields, if you aren't clear about it, they are exactly 90 degrees to each other in three-dimensional space. And to describe that they're 90 degrees in three-dimensional space with each other, we use the term orthogonal. All right. So no matter how you look at it, in whatever perspective, it's always going to be a 90-degree relationship. So that's something to keep in mind. Okay. The B fields will never be parallel to the conductor. It's a common mistake a lot of students make. Okay. The B fields will never be parallel to the conductor. It'll always be 90 degrees to it or orthogonal to it, circling kind of like an orbit all the way around it. Now, this is a demonstration that you can do if you have a high current power supply, wire that can handle it before it overheats, and you're able to stab the metal on top of a piece of glass to do it. And I do have that equipment, but every single time I do the demonstration, the results are usually terrible. And that's because my power supply can only output at most 5 amperes when I need something, probably around 30 to 40 amperes passing through it. And that's when I'm going to see reasonable results. So what I would do, I'm just telling you on video, that you would have a conductor like this, you connect it to a very high-powered current supply, all right, and you're letting the current flow through, and then you put a piece of paper right through it. So you stab this pretty much through a piece of paper. Then you'll take the iron filings and you'll sprinkle it on top, smell all the crazy nasty smoke because everything is overheating, and then you quickly turn off the power supply, hoping to see something cool on top. And if you use your imagination, you can somewhat see concentric circles of dots that create these little orbits around it. And it's not the best of demonstrations. That's why I'm not going to show that to you. But I was at a science center out on the West Coast, and they had a very similar setup, except they didn't want you to play with iron filings. Instead, they placed tiny little magnetic compasses all around the conductor. So let's play that video and see what the outcome is. Now, mind you, this setup has been played with by thousands of kids, and they've probably mutilated the magnetic directions of all the little compasses. So originally, all the compasses should all be pointing properly to magnetic north. You'll probably see a handful of them pointing the wrong way because they've been ruined over time and they've never properly recalibrated. But nevertheless, at the beginning of the video, you'll see that all the magnetic fields are all pointing in one direction, which is to where magnetic north is relative to the Earth. And then after I allow current to pass through, you'll hear a big clunk because a lot of current going through. And yes, the cable in the center does get rather warm. I didn't touch it, but it does get rather warm. And then you'll quickly see all the little compasses all line themselves up, forming these awesome looking concentric circles. So here we go with the video. That's my hand. And there's the clunk. You guys see that? Isn't that beautiful? Yeah, I can play it one more time. Okay. So here it is at the beginning. You can see that they're all lined up relative to North Pole. Once I allow current to pass through, boom. The ones that are actually still working, because I see some of them are just dead, they'll all line up and they'll form concentric circles around the conductor. And there it is turned off again. And that's a demonstration. This one is called, what's the science center called? Exploratorium, the Exploratorium in San Francisco. Definitely recommend you guys check it out if you guys have a chance. Okay, so here's a snapshot of that frame over there. And you can see that, yes, all of the little compasses, they're all in alignment with each other. They should be facing the same direction. However, some of them, unfortunately, again, they got messed up because thousands of kids are playing with it. So they're not perfectly pointing that way. But you can still see these concentric circles. Okay, and yeah, you can see that there are some rogue ones. Like this guy's probably a rogue one. Let me look at the rest. This is probably another rogue one. I'm guessing that's a rogue. Simply because it's not facing with the majority. So I'm just trying to look at the majority. And yeah, those two probably aren't facing the right way. But the rest are all facing the right direction, right? They're all showing some direction like that. Now, here's where you got to be careful. It's just like back to magnetic Earth, okay? if the Earth's magnetic pole is actually magnetic south on top and north down below, so even though the field lines are going this way, your compass will always point the opposite way. So your compass will never be lined up in the same direction as the true magnetic field lines. So in this case over here, if we say the majority wins, we might accidentally think that the B field lines are traveling this way, but in real life, if this was drawn properly, the B field lines are all traveling this way, okay? Because they'll be opposing in direction because opposite B field lines attract each other, okay? And if that's true, then we can do the reverse right-hand rule, where our fingers indicate the direction of B fields. So if you look at this is you're looking at it from slightly overhead, you can see that the B fields are kind of curling like this, and your thumb points to where the current is flowing. So in this setup over here, we can assume that the current is flowing upwards. Okay, so it's coming from somewhere down underneath the table, traveling inwards, traveling upwards, and these are the concentric circles that are formed, and they're all traveling counterclockwise from this perspective. And here is where it brings up a problem. Okay, how do you properly label this on a test? Okay, how would you draw this out? Well, you have no choice but to draw it out. Because you imagine if this plate over here, I know it's made up of wood, but it was made up of plexiglass, the direction of B fields is based upon your perspective. If you're looking at the plexiglass from above, then yeah, it looks like it's still circling counterclockwise. But if you're a short little kid and you can't see from above and you're looking from down below, you're going to see the B fields traveling the other way around. So when it comes to the answer key in your homework, yeah, I'm going to write down clockwise and counterclockwise because I want to fit the answer key inside here. But the proper way to label the direction of the B fields is by graffitiing on top of the diagram. So you're going to take the diagram and you're going to draw on top of it to tell the reader which way either the B field lines are traveling or the direction of current. Okay, so that's our next exercise. But before we get there, one more thing I need to point out is that you'll see these problems are all three-dimensional, right? All the B fields lines, they'll create circles all on a surface. They will form magnets. Look at magnets, okay? They will all form a plane, and that current will always be orthogonal to the plane. In other words, it's going to be a three-dimensional problem. So how do you describe a three-dimensional problem on top of a two-dimensional piece of paper? That's when we have to add another notation. Okay, so here's the symbolic notation to describe fields or vectors that are pointing either out of the page or into the page. And we go by this dot x notation, where dot indicates that the force, the field, or the current is pointing out of the page, like right towards you guys. Meanwhile, an X is where it's coming out of the page. No, sorry. Yeah, no, dot means it's coming out of the page. Sorry. I'm just showing it in the wrong perspective. I should be standing where the camera is. Okay. So if you see a dot, that means that the current is coming towards you. And if you see an X, that means that the current is leaving away from you, or the force is going away from you and going into the page. I'll give you guys a moment to jot that down. All right. So the question is, like, how do you memorize this stuff over here? Because at some point, you're stressed on the test. You can't look at your notes, and you're wondering, well, am I supposed to use a dot or an X here? And the memory aid for this is to imagine yourself as an archer with his arrow and bow. So here's my ghetto version of an arrow, but I hope you get the idea of this. All right. If at any point where you see the front of the arrow pointing towards you, that's when the vector is pointing towards you because you see a dot. Okay. So dot means that it's coming towards you. Okay. On the other hand, if you're the archer itself and you're this way, well, now you have this entire bow or arrow, sorry, pointing away from you. And as it's moving away from you, all you see as it's moving away from you is the X. Okay. So that's the memory aid. The dot indicates that the current, the B field, or whatever vector it is pointing towards you. That's why you see a dot. And if you see an X, that means it's moving away from you and going into the page. That's the memory aid. Okay, and with that memory aid in mind, let's start solving tonight's homework questions. Sure, I'll give you guys another moment in jotting this down and trying to predict it out. And yeah, I'll start the timer again, 2 minutes. Okay, I hope that's enough time for you to jot down these 3 diagrams. So let's solve it together. And yes, there are some students who are wondering, how do you know whether you're supposed to state it as clockwise or counterclockwise? Again, you're not supposed to state that. So don't write down clockwise or counterclockwise. Instead, you're supposed to draw on top of the diagram to tell the reader what the answer is. And you'll see what I mean as we start drawing these pictures out. Okay, so the first case over here, that blue circle in the middle, that indicates the fact that you're looking at a conductor straight on like this. Okay, and the dot is just remind you that the current in the setup over here is pointing towards you, the viewer. Okay, so as the current is pointing towards you, remember you have to use your right hand to determine the direction of the B fields, and then you'll have the thumb pointing towards where your eyes are, right? Because you're looking at it from this perspective as the dot's coming towards you. So it's coming towards you. You can see that the B fields are circling towards the left at the top and towards the right down below. All right. So when you label this, you're going to go off and draw these little chevrons. Okay, these tiny little arrows, and that's to tell the reader which way the B fields are traveling. So just draw, a handful of them, anywhere from, 6 to 12 of them, and that's more than enough to tell the reader what it is. The last thing you want to do is remind the reader that those are the B fields. And that's the answer to this question here. That's it. Now, on your answer key, how will it describe it? Well, the thing is that you'll see here, the answer to this is a diagram. So how do you answer a diagram then, other than by drawing it out? So on your homework tonight, guys, once you're done with it, please check with the answer key in Google Classroom. But on the bottom of your sheet of paper, I did write down CW and CCW. And that's just to tell you that if you look at this holistically yourself, when you look at your answer key, in this first example, it's going to appear to be traveling counterclockwise. Okay, so when it comes to test time, guys, do not write down counterclockwise. Just draw the arrows and you're fine. The purpose of CCW is because that's the only way I can fit the answer key in this space over here. Okay, guys? So let's try out the next one. Okay, what is the answer for the next one? Well, right now we can't tell if the current is coming towards you guys or away from you. But what you do know is if you place your hand on top of the screen right here, you can see that your fingers kind of look like this, at least from my perspective. And then from your perspective, it's going to look like that. Yeah, so that's what you're going to see, right? You're going to see that the B fields are going to the right on top. They're traveling downwards on the right-hand side. They're traveling to the left at the bottom, and they're traveling upwards on the left-hand side. And in this entire rotation like this, your thumb is constantly pointing into the piece of paper or into the wall. Okay, so to tell the reader that the current is going into the wall, again, the memory aid for this is look at an arrow. If the arrow is going into the wall, then all you see is the X. All right, so the correct answer for this one over here is X. To tell the reader that X marks the spot. You're going into the page. Okay, and that is the direction of current. So the direction of current is going into the page. I'm going to write it inside here just for clarity's sake. Okay. So the current's going into the page, and the outside, these arrows here are representing the B field. One more example, and this one over here is a perspective diagram. And in the perspective diagram, you can see that the conductor is through the front down here. And because it breaks off at the top, it looks like it's behind. And if you're having troubles trying to draw that out, what you do is that you'd start just drawing a bunch of C's, where it's going to disconnect at the back. And that's how you tell the reader that that these B field lines, even though they're creating a plane, the plane is out through the front and through the back. It is, yeah, it's going through the back. So it should look more like that. Sorry, not the best of artists. And if you want to give thickness to it, then by all means give thickness to it so it makes a lot more sense. By all means, right? Because you can see that once I give thickness to it, it starts resembling more of that picture there. There you go. Okay, so what's given to you right now is the current is flowing from top to bottom. So we know that the current is flowing this way. Okay, so that's the direction of current. I'm going to erase my sketch there. It does help if you have some sort of, object around, even if it's your pen. Your pen will work just fine. I'll just use this because it's nice and big. So the current is going down the page, all right? And according to your hand over here, you can see that according to the diagram, the current is moving to the left, at least in front of this orbital path that it looks like. Okay, so it's traveling towards the left. So that's why I have my chevrons pointing to the left. And then they'll be traveling towards the right through the back. So I'll include some arrows behind to tell the reader that the B field lines are traveling out through the back. Okay, and that's how you would answer this question here. You just draw that out, and then you'd label to the reader, telling them this is the direction of the B fields. Any other questions, guys? because other than that, that's it for today's lesson. All right, so for tonight's homework, finish off on course pack page 55, all of it. Again, you can find the answers in Google Classroom, and I guess I'll catch you guys in the next episode then, if there are any other questions. Bye for now. Oh, there's a question. Cancel. Yeah, may as well record that because maybe it's an important question. So ask away or type it away.
Could you just explain how you found the direction of the arrows again? Or-
Okay, I can repeat this one more time. Just remember, this is all recorded as well. But just in case you want to see it one more time, let's go through this. So again, the example on the left, all you're given is a dot. And that dot indicates current. So the current is coming out of the page, right to your nose, right? So as it's coming right to your nose, you look at your hands, and you see that as you're playing your virtual trumpet, all your fingers are curling to the left up on top. So that's how I know that the chevron arrows are pointing to the left on top. And as I curl my hand around, I can see that the B fields are moving towards the right down below. Because you can see that these B fields, they create a loop, and they always cycle in the same orientation. And the orientation is based upon the direction of current. Because if I flip the current around, then the B fields will flip the other way around, which is exactly what's happening in diagram number 2. Because if you look at diagram number 2, now the arrows are pointing the opposite way. So even before even using your hands, you already know it's going to be an X. But let's go through it formally. All right. So with the second diagram, again, you're holding your hand out in such a way that your thumb is pointing into your piece of paper. Okay. So you're pointing into the piece of paper like this. Because this is the only way to ensure that your B fields are traveling to the right, up above, and down through the bottom. Right. It's the only way you can match up with the diagram, by holding it this way. So you know that the current's going into the page, and to tell the reader that the current's going into the page, you're going to denote it with an X, because the X tells you that the current, or the B fields, or whatever vector it is, that it's pointing that way. And that's why we place a letter X for the second one. Again, the third one is just the three-dimensional picture. And a three-dimensional picture, you kind of have to use your imagination in figuring out where the arrows are pointing. Okay, so first off, it tells you that the current is flowing from top to bottom. So the current is traveling from on top and traveling through the bottom like so. And I'll denote it with the letter I to tell the reader that this is the direction of current flow. Okay, pick up a piece of metal, if you have one, or a pencil, and then start holding it in that orientation. And when you hold in this orientation, you'll notice that your fingers, they all point towards the left in front of that stick, and they point to the right behind the stick. So that's how you're going to try to draw this. And that's your answer. Okay, because here's the problem about the last one. How do you know if it's clockwise or counterclockwise? It depends upon how tall or how short you are. Because if you look at it from above, yeah, it looks clockwise. But if you're short, it looks counterclockwise. And that's why I don't want the answers to be clockwise and counterclockwise when you state these at the end. All right, I want you to physically draw on top of it, and as well label what the arrows represent. So that represents B fields. This X describes current, and these arrows out here represent your B fields yet again. Okay, I hope that answers that question. Any other questions before I stop the recording? All right, then best of luck in your homework, and I'll catch you guys in the next episode.